Okay, this is a supplementary video I've decided to make based on some questions I've been getting from email. It's real short. I'm just calling this Redox, but I'm going to show you a couple things that are presenting some problems for some students that have contacted me. The first thing I want to talk about is this table once again. I think most people have probably gotten down the basics of, these are the best oxidizing agents up here and these are the best reducing agents down here. But one of the things you're often asked is, how the reduction potential changes if you change a particular, replace one species for another. And there's a question like that actually in your book. I forget, it's like 20 something. But let's say we have zinc paired with copper, and we get a particular potential there based on that. Um, Now, if you look at these two pairing up and say we're going to have solid copper, solid zinc, and copper solution and zinc solution, doesn't matter. It could be just copper sulfate and zinc sulfate. That's fine. Our potential then, remember, is always this equation here. The E naught of the cell is equal to the E naught, and however you write this, the cathode or the reduction, it doesn't matter, the reduction minus the E naught of the oxidation. Remembering that the negative sign serves to flip the oxidation one. And that's the one that's going to be lower. So in this case, for copper, it would be 0.342 minus a negative 0.762, and this would be your potential. Now let's say I replace copper with nickel. Now instead of copper, I'm going to use nickel, which is down here. Now you can do the math again, and your potential will be less. You can actually do the math, but the potential will be less. And the way to look at this is the difference between the oxidation and reduction reaction is the potential energy that you're going to get. Just think about like dropping a waterfall, the height at which it drops. Dropping from here to here gives you a greater energy than dropping from here to here. It's no different. Now, the math will tell you that if you plug it in, but if you're not asked to actually calculate it, you're asked to explain why or does it decrease or increase, that's the reasoning. If I switch nickel from copper, these two are closer together now, and therefore the potential will be less. So that's important to understand. The only other thing I want to do is I want to take you through two calculations again using this flow chart that I've given you. So I'm actually going to do for you problems 74 and 75, which are in the back of the book. So I'm not going to rewrite them. You can just look them up. So for 74, you're starting with math. I think both of them you're starting with mass. 0.750 grams, okay? And what you're asked for basically is, the amperage, okay? These are given time also. Okay, so following our notation here, we're going to go from mass of substance to moles of substance using the molar mass. And this one happens to be platinum that we're dealing with. So it's just the molar mass of platinum. So that's the 195.08 grams in 1 mole. And if you look at the reaction that's given to you, this is the reaction. It's basically platinum Cl4 2 minus plus 2 electrons. So you know there's 2 moles of electrons being transferred, and that ultimately gives you platinum solid. So here platinum's 2 plus because this is 2 minus here, and chlorine's minus 1, so this is actually 2 plus here, but you can tell from this, obviously. So it's 2 electrons being transferred. So that would be your next step, would be 2 moles of electrons for every 1 mole of platinum. Now, how do you remember this? Well, you got to somewhat commit this to memory, but the way to think about it is, okay, grams to moles, and I need to get to electrons. I'm always interested in the current, the electrons, okay? And then you're going to use the Coulomb's, the Faraday expression to take you to the next step, 96,500 coulombs per mole of electron. So you can see now where I'm at here. I've gotten rid of grams, I've gotten rid of moles, I've gotten rid of moles of electron to coulombs. Now, realizing my next step, if you will, would be times, if you will, 1 over 2.5 hours, your time, because coulombs per time is an amp, but you need per second. So we're going to have to do 1 hour is 3,600 seconds. Okay, and this will give you units now of, let's cross these out so we don't get confused. Hours are gone. What we get is ultimately equal to 0.082 coulombs per second, which is equal to amps. Those are the same units, and that's what the question is asking. So that's how you do one of these problems, okay? And we did a couple already, but I'm going to do one more for you. Question 75. These are in the back of your book, 74 and 75. I can't remember if I signed both or not. I think I did, but this one, there's only one little tricky part to it. You're given 4.10 grams, but you're told only, you're told only 50% of it has reacted. So effectively, that's what you're asked for. So you want 50% of 4.10 grams. So you wind up with 2.05 grams. Otherwise, we're doing the same thing now. 2.05 grams times, and this was the nickel oxide hydroxide. If you look at the problem, so it's 1 mole is going to be 91.70 grams. Excuse me. This is the same one, same battery that we actually did an example of before with that molar mass. In this case, it's literally nickel plus 4 going to nickel plus 3. So it's going back and forth because it's rechargeable between plus 3 and plus 4. So it's only one electron being transferred, because what you have here is this. You have nickel and you have nickel. Now OH is minus 1. So I'm sorry, plus 2 and plus 3, not plus 2 and plus 4. So NiOH2 is going to be plus 2 here, and this would be plus 3. So it's 1 mole of electron here is what we need for every 1 mole. Okay, and then you can do your 96,500 coulombs per mole of electron. Okay, and then times. The only difference here is we actually have the amps and we want the time. So looking at my units then, once again, grams are history, moles are history, moles of electrons are history. I've got coulombs, and I'm interested in this case, time, knowing that an amp is a coulomb per second. So if I do, so I think we were given 2 amps, which is 2 coulombs per second. So if I divide by that times 1 over 2.00, and I'm going to write it as coulombs per second. It's amps. Because remember, amp is a coulomb per second. That makes it easy for me to realize now that I've gotten rid of my coulombs, and my answer is going to be in seconds. I believe maybe they asked for it in minutes. You can do that conversion yourself, but basically, 60 seconds per minute, of course. And you wind up with 18 minutes. So that's just my short redox video to help you with a couple of these calculations. You'll probably see 2 of these on your exam, one starting with mass and maybe one going in the other direction. Who knows, but you should be comfortable with these. And then, of course, the understanding of the table and the reduction potentials is important. So make sure you look this stuff over.